I want to tell you the strangest fact about light. Not the most famous fact that light travels at approximately 300,000 kilometers per second, that it takes 8 minutes to reach us from the sun, that it bends around massive objects, and that this bending was confirmed by Eddington's 1919 solar eclipse expedition, that it carries the energy that drives every photosynthetic organism on Earth, that it is simultaneously a wave and a particle in ways that have challenged our deepest intuitions about the nature of matter for over a century. Those are remarkable facts, and I've described them in earlier videos. The fact I want to tell you now is less well-known and, I think, stranger than any of them. The fact is this: from the perspective of a photon, from the reference frame of a particle of light, it takes no time to travel from its source to its destination. None. Zero. The photon that left the star 10 billion light years away, that has been traveling for 10 billion years by your clock, has experienced no time whatsoever on its journey. From the photon's perspective, it was emitted and absorbed at the same instant. There is no duration. The journey that spans 10 billion years in our experience spans zero time in the photon's experience. And there is a related fact that is equally strange. From the photon's perspective, the distance between its source and its destination is also zero. The 10 billion light years that separate the star from your eye are contracted from the photon's frame of reference to zero distance. The photon does not travel through space. It is, in some precise sense, simultaneously present at every point along its path. These facts follow directly from special relativity. They are not metaphors, not approximations, not philosophical interpretations. They are mathematical consequences of the Lorentz transformations applied in the limit of a particle moving at the speed of light. But they raise an immediate puzzle. If the photon experiences zero time and zero distance on its journey, what does it mean to say it is a particle of light traveling through space? What is traveling if there is no time and no distance? And how can we make precise sense of the photon's perspective when, as I will show you, the photon does not actually have a valid reference frame in the technical sense of special relativity? These questions do not have easy answers. In fact, working through them carefully leads to some of the most profound insights in all of physics about the nature of causality, about the geometry of space-time, about the relationship between zero rest mass particles and the causal structure of the universe. Let me start at the beginning with the specific numbers, because the concreteness makes the strangeness more vivid than the abstraction does. The sun is 150 million kilometers from Earth. Light travels at 299,792,458 meters per second, or approximately 300,000 kilometers per second. The time for a photon to travel from the sun to Earth is 150 million kilometers divided by 300,000 kilometers per second, which is 500 seconds, or approximately 8 minutes and 20 seconds. When you look at the sun, you are seeing what the sun looked like 8 minutes and 20 seconds ago. The nearest star to the sun, Proxima Centauri, is 4.24 light years away. 1 light year is the distance light travels in 1 year, approximately 9.46 times 10 to the 12 kilometers. Proxima Centauri is approximately 4 times 10 to the 13 kilometers away. Light from Proxima Centauri takes 4.24 years to reach Earth. When you look at Proxima Centauri in the night sky, you are seeing what it looked like 4.24 years ago. The Andromeda Galaxy is approximately 2.537 million light years away. Light from Andromeda takes 2.537 million years to reach us. When you observe Andromeda, you are observing the galaxy as it was before modern humans existed. The most distant galaxies visible to the James Webb Space Telescope are at distances exceeding 13 billion light years. When Webb detects these galaxies, it is detecting light emitted when the universe was less than 1 billion years old. All of these photons, the one from the sun that took 8 minutes, the one from Andromeda that took 2.537 million years, the one from the distant galaxy, detected by Webb, that took 13 billion years, share one property? From the perspective that special relativity allows us to approach by taking the limit of the Lorentz transformation as the velocity approaches c, every one of these photons accumulated 0 proper time on its journey. The photon from the sun and the photon from the 1,3 billion light-year galaxy both arrived with 0 proper time. Despite the coordinate time of their journeys differing by a factor of 13 billion divided by 8 divided by 525,960, a factor of approximately 10 to the 13th. In coordinate time, the journeys are astronomically different. In proper time, they are identical. Both are 0. This is the strangest fact about light. Let me now derive it precisely. The Lorentz transformation relates the space-time coordinates measured by 2 observers in relative motion. If observer A is at rest and observer B moves past at velocity v in the x direction, the time interval delta tau measured by B's own clock, B's proper time is related to the coordinate time interval delta t measured by A by delta tau equals delta t times the square root of 1 minus v squared divided by c squared. This can be written as delta tau equals delta t divided by gamma, where gamma equals 1 divided by the square root of 1 minus v squared over c squared. The factor gamma is always greater than or equal to 1 for v less than or equal to c. For v much less than c, gamma is approximately 1, and the proper time equals the coordinate time. For v approaching c, gamma becomes large, and the proper time becomes much less than the coordinate time. For a muon at 99.9% of c, gamma is approximately 22. And the muon's clock ticks 22 times more slowly than coordinate time. Now apply this formula to a photon, which moves at exactly v equals c. Substituting v equals c, delta tau equals delta t times the square root of 1 minus c squared divided by c squared equals delta t times the square root of 1 minus 1 equals delta t times 0 equals 0. For any coordinate time delta t, no matter how large, the proper time delta tau is 0. The calculation is exact. A photon traveling for 1 microsecond of coordinate time accumulates 0 proper time. A photon traveling for 10 billion years of coordinate time accumulates 0 proper time. The same calculation applies to spatial distances. The length of a measuring rod measured by an observer moving at velocity v relative to the rod is contracted to L divided by gamma, where L is the rest length of the rod. For v approaching c, the contracted length approaches 0. For v exactly equal to c, the contracted length is exactly 0. So from the perspective that we approach by taking v to c, both the time elapsed and the distance traveled are 0. The photon's journey, however long in coordinate space and coordinate time, spans 0 proper time and 0 proper distance. Now I need to confront the puzzle directly. What does it mean to speak of the photon's reference frame? The Lorentz transformation is valid for observers whose velocity relative to each other is strictly less than c. For v equal to c, the factor 1 minus v squared over c squared equals 0, and the square root of 0 is 0, which means gamma equals 1 divided by 0 equals infinity. The Lorentz transformation breaks down. The quantities it is supposed to transform become undefined or infinite. This is not a technical limitation that might be resolved with better mathematics. It is a fundamental structural feature of special relativity. The postulate that the speed of light is the same for all inertial observers implies that no inertial observer can move at the speed of light. If an observer moved at c, the light in their reference frame would need to be both moving at c relative to them and stationary relative to them, which is contradictory. So the photon does not have a reference frame in the technical sense. The statement that the photon experiences 0 time and 0 distance is a limit statement. It describes what happens as you consider observers moving at velocities approaching c. In that limit, the proper time accumulated on any finite coordinate time journey approaches 0. The The limit is 0, but the limit is not achieved by any physical observer. This is an important and often missed distinction. The strangest fact about light is not that the photon moves through a reference frame in which time does not pass. The strangest fact is that the photon is excluded from the reference framework entirely, and the limit of the proper time as the velocity approaches c is 0. The photon exists at the boundary of the theoretical framework that describes all massive particles, and that boundary is characterized by 0 proper time and 0 space-time interval. Ready to change how you see the world? The properties of light, its 0 rest mass, its invariant speed, its exclusion from the reference framework, and the 0 proper time that characterizes its excluded but limiting perspective are among the deepest principles in my book about the fabric of reality. Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now develop the physical meaning of the photon's 0 proper time more carefully, because even though the photon has no valid reference frame, the mathematical limit does have profound physical content that manifests in real and measurable ways. Consider a physical process that unfolds in the photon's frame. For example, consider a photon that is produced in a nuclear reaction in the core of the sun, travels through the solar interior, an additional complex story involving absorption and re-emission in the dense solar plasma, emerges at the sun's surface, travels through interplanetary space for 8 minutes by Earth's clocks, and then is absorbed by a photoreceptor molecule in the retina of an eye on Earth. From the perspective of any observer whose rest frame is not the photons, from our perspective on Earth, or from the perspective of a spacecraft moving at any velocity strictly less than c, the photon's journey from the sun's surface to Earth takes 8 minutes and 20 seconds. The photon travels 150 million kilometers. Now ask, does the photon age during this journey? For a massive unstable particle, the answer is yes. The particle's proper time accumulates, and unstable particles decay with a rate determined by their proper time. For a muon traveling at 99.9% of the speed of light, the proper time elapses at 1/22, the rate of coordinate time, allowing the muon to travel 22 times further than its rest frame half-life would suggest before decaying. This is confirmed by the cosmic ray muon observations that I described in the block universe video. For a photon, the proper time is 0. The photon does not age on any finite journey. This means that if a photon were carrying a molecular clock, if somehow the photon's internal structure were a clock that measured proper time, that clock would show 0 elapsed time regardless of the coordinate time of the journey. More concretely, imagine a molecule that is excited to an unstable electronic state and then attached to a photon in some quantum sense. If the molecule's decay rate is determined by the proper time of the photon, the molecule would never decay regardless of the journey's coordinate time duration. The photon's proper time is 0, so no time passes in which the decay could occur. This is, of course, an idealized thought experiment. Molecules cannot literally be attached to photons in the way described. But the concept is physically meaningful in the following sense. The photon carries no internal clock. A massive particle carries an internal clock. Its rest frame time passes as proper time accumulates, and this proper time governs all internal processes, including the decay of unstable particles. A photon with 0 rest mass carries no such clock. It has no internal processes that unfold with respect to proper time. Because it has no proper time, this is connected to a deep fact about the photon's quantum state. In quantum field theory, a single particle state is characterized by its energy, momentum, and spin state. For a massive particle, there is a rest frame in which the energy equals the rest energy mc², and the momentum is 0. The particle's quantum state in the rest frame is particularly simple. For a massless photon, there is no rest frame. The photon's quantum state is always characterized by non-zero energy and non-zero momentum, with the constraint E equals pc. There is no simplest frame in which to describe the photon, because the simplest frame, the rest frame, does not exist. This absence of a rest frame is connected to the photon's two polarization states rather than the three polarization states a massive spin one particle would have. The third, longitudinal polarization state that a massive spin one particle has in its rest frame simply does not exist for the photon, because the photon has no rest frame in which to define the longitudinal direction. The masslessness of the photon reduces its polarization states from 3 to 2. The connection between 0 rest mass, 0 proper time, and the reduced polarization states is not coincidental. It is a consequence of the Lorentz symmetry of the theory. The Lorentz group, the mathematical group of space-time symmetries, has different irreducible representations for massive and massless particles. Massive particles belong to representations labeled by their rest mass and their spin. Massless particles belong to a different class of representations labeled by their helicity, the projection of their spin along their direction of motion. The photon has helicity +1 or -1, corresponding to right and left circularly polarized states. There is no helicity 0 state for the photon, which would correspond to the longitudinal polarization that massless particles cannot have. This mathematical structure, the representation theory of the Lorentz group, is the deepest reason why the photon has two polarization states, why it has no rest frame, and why it has 0 proper time. All three properties are consequences of the same underlying mathematics. The photon is a massless helicity, one representation of the Lorentz group. Let me now develop the most precise version of what it means for the photon's worldline to be a null geodesic, because the geometry of null geodesics is what connects the 0 proper time of the photon to the causal structure of the universe. In the four-dimensional space-time block, every point is an event, a location in space at a moment in time. From any given event, there are three types of directions in space-time. Time-like directions point toward events that could be causally influenced by the starting event or could have causally influenced it. Space-like directions point toward events that are outside the light cone and are causally disconnected. Light-like or null directions point exactly along the light cone toward events that are connected by a light signal. The worldline of a massive particle is a time-like curve. It always points in a time-like direction, meaning it stays inside the light cone at every event it passes through. The particle can move through space, but its velocity is always less than c. At any event on the worldline, the future pointing tangent vector is inside the forward light cone. The worldline of a photon is a null curve. It points exactly along the light cone at every event. The photon's velocity is exactly c, and the tangent vector to its worldline lies on the light cone boundary, neither inside nor outside. The photon's worldline never enters the interior of the light cone, but always rides its boundary. The space-time interval along a null curve is 0. If you integrate the Minkowski line element, ds² equals c²dt² plus dx² plus dy² plus dz² along a null curve, you get 0, because at every point the integrand is 0. A null curve has 0 Minkowski length. In the precise geometric sense of the Minkowski metric, the curve has 0 extent. This is one of the most remarkable properties of the Minkowski metric. It assigns 0 length to curves that have enormous extent in coordinate space. A null geodesic from a galaxy at redshift z equals 10, emitted when the universe was 470 million years old, arriving at a telescope on Earth today, spans 13.3 billion years in coordinate time and approximately 46 billion light years in coordinate distance, accounting for the expansion of the universe. Yet the Minkowski interval along this null geodesic is 0. The 0 Minkowski length of the null geodesic is the geometric statement of the 0 proper time of the photon. Proper time is the square root of the magnitude of the Minkowski interval along the worldline divided by c. If the Minkowski interval is 0, the proper time is 0. The two statements, the photon's worldline is a null, geodesic, and the photon has 0 proper time, are mathematically equivalent. The light cone structure of spacetime, which is defined by the set of all null geodesics through each event, is the fundamental causal structure of the spacetime block. It determines which events can causally influence which other events. The photon's worldline is a null geodesic, so the photon's emission and absorption events are exactly on each other's light cones. They are causally connected, but just barely. They are connected by the minimum energy path, the path that travels at exactly c and accumulates 0 proper time. In the Penrose conformal diagram representation of spacetime, null geodesics are represented as straight lines at 45 degrees to the time axis. Every photon worldline, regardless of its coordinate distance, is a 4-5 degree line in the conformal diagram. The conformal diagram compresses the infinite spacetime block into a finite region using a mathematical transformation called conformal rescaling that preserves the causal structure, the light cone angles, while distorting the coordinate distances. In the conformal diagram, the Big Bang is represented as a horizontal line at the bottom, and the future boundary of the spacetime is represented as a horizontal line at the top. Null geodesics are 4-5 degree lines connecting events. The entire observable universe, all the events from which light has had time to reach us since the Big Bang, is the region inside the past light cone of the current moment, represented in the conformal diagram as the region below a specific 4-5 degree triangle. The conformal diagram makes vivid the extent of the observable universe. It is bounded by the null geodesics, the photon paths that reach us from the Big Bang. And every one of those photon paths, spanning 13.8 billion years of coordinate time, is a null geodesic with 0 Minkowski length. Every photon that has ever reached us from the universe's history connected us to its source through a path of 0 proper time, a connection that spans the entire history of the observable universe while accumulating 0 experience of time. This is the geometry of the universe as experienced by light. The universe, from the photon's excluded but limiting perspective, is not a vast structure spread over billions of light years and billions of years. It is a structure in which every emission event and every absorption event are, in the Minkowski metric, at 0 spacetime distance from each other. The photon connects them not by traversing a distance, but by being, in the precise geometric sense, the same event in space-time as both its emission and its absorption. Let me now describe what this means for the way we receive information from the universe, because the 0 proper time of the photon is not just an abstract geometric fact, but has specific implications for every observation of the cosmos. Every observation in astronomy is an observation of photons. When a telescope detects a galaxy at redshift z equals 2, it is detecting photons that were emitted approximately 10.3 billion years ago. When a radio telescope detects the cosmic microwave background, it is detecting photons that were emitted approximately 4 billion years ago, when the universe was 380,000 years old. When your eyes detect starlight, they are detecting photons that were emitted years or centuries or thousands of years ago. In each case, the photon that arrives at the detector has accumulated 0 proper time on its journey. The photon emitted from the surface of last scattering 13.4 billion years ago and arriving at a microwave telescope today has experienced 0 time between emission and detection. From the photon's excluded but limiting perspective, its emission and detection were the same event. This means that every observation of the cosmos is an observation of the universe at 0 proper time from the photon's perspective. The information that astronomical observations extract from photons is information about events that, from the photon's perspective, just happened, are happening, will happen at the same instant as the detection. The photon is not carrying a message from the past. It is connecting the past emission event to the present detection event through a path of zero space-time distance. The emission event and the detection event are, in the Minkowski metric, the same space-time location. The information encoded in the photon's frequency, polarization, and direction is the complete information carried by this zero-length connection between two events in the space-time block. When you look at a distant galaxy and see photons that left it 1 billion years ago, you are not receiving a message from the past. You are observing the zero space-time length connection between the galaxy's surface of emission 1 billion years ago and your retina right now. The galaxy's past and your present are connected by a null geodesic of zero Minkowski length, and the photon is the physical realization of that connection. This reframes the poetic statement that stargazing is time travel. It is not exactly time travel because the photon has not traveled through time. The photon has connected two events in the space-time block, the distant galaxy 1 billion years ago and your eye right now through a path of zero space-time distance. You are not looking into the past. You are observing a zero-distance connection to the past. The universe, from the photon's perspective, is not extended in time. It is a network of zero space-time length connections, each one a null geodesic connecting emission events to absorption events, spanning what seem like vast distances in eons of time from our time-like perspective, but spanning zero from the photon's null perspective. The 12 principles in my book include exactly this: the radical shift in perspective that comes from understanding the geometry of null geodesics and what it implies about our connection to the universe through light. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. The first consequence is the impossibility of giving the photon rest mass. The proper time along a world line is directly connected to the particle's rest mass through the relation between energy, momentum, and rest mass, E² equals P² c² plus m² c to the 4th power. For a massless particle, a particle with m equals 0, the energy equals the magnitude of the momentum times c. Such a particle must travel at exactly c. It cannot travel slower, because a massive particle moving at c would require infinite energy, and it cannot travel faster because faster than light travel violates the causal structure of space-time. Let me now place the zero proper time in historical context, because the path from Newton to quantum electrodynamics shows how each revolution brought us closer to this strangest fact. Newton believed light consisted of tiny corpuscles, particles traveling in straight lines. His optics of 1704 established the corpuscular theory. Young's double-slit experiment in 1801 overthrew it, showing interference fringes that could only be explained by wave behavior. Fresnel's mathematical diffraction theory in 1818 completed the wave picture. Maxwell's 1,873 equations unified all electromagnetic phenomena and showed that the speed of the predicted electromagnetic waves equaled the measured speed of light. Light was an electromagnetic wave. Hertz confirmed the prediction with radio waves in 1887. Then Einstein's 1,905 photoelectric paper proposed that light is also quantized. The photoelectric effect, the ejection of electrons from metals by light of sufficient frequency, regardless of intensity, could not be explained by a pure wave theory. Each photon carries energy h bar omega. If that energy exceeds the work function of the metal, an electron is ejected. If not, none are, regardless of how bright the light is. This is the particle aspect. Compton's 1,923 discovery sealed it. X-rays scattered off electrons show a wavelength shift given precisely by the formula treating the X-ray as a particle with momentum h bar k, transferring momentum to the electron. The Compton formula, delta lambda equals h bar divided by m EC times 1 minus cosine theta, can only be derived by treating the photon as a particle. The reconciliation came with quantum field theory. In q²dt, developed by Feynman, Schwinger, and Tomonaga in the late 1940s, the photon is the gauge boson of the U1 gauge symmetry of electromagnetism. Massless spin 1, 2 helicity states propagating along null geodesics. q²dt predicts the anomalous magnetic moment of the electron to 12 decimal places, better than any other physical prediction in history. The zero proper time of the photon is built into q²dt from the start. The photon propagator for a real photon is derived from the massless dispersion relation, which puts the photon on the light cone on the null geodesic with zero proper time. The photon's zero rest mass is directly connected to its zero proper time. A particle with non-zero rest mass has a reference frame in which it is at rest. And in that frame, its proper time accumulates at the same rate as coordinate time. A particle with zero rest mass has no rest frame. It always moves at c and cannot be brought to rest. Its proper time along any segment of its worldline is 0. The Higgs boson, which was discovered at CERN in 2012, gives rest mass to the massive particles of the Standard Model through the Higgs mechanism. But the photon does not couple to the Higgs field in the way that massive particles do. The photon remains massless. The specific structure of the electroweak theory requires the photon to be massless in order to preserve the U1 gauge symmetry of electromagnetism. If the photon had a mass, even a tiny one, electromagnetism would be fundamentally different. Coulomb's law would have a finite range rather than infinite range. And the magnetic and electric fields would have a longitudinal polarization mode in addition to the two transverse modes that are observed. The masslessness of the photon is not an accident. It is a consequence of the gauge symmetry of electromagnetism, which is one of the most fundamental principles in the Standard Model. The gauge symmetry requires the photon to be exactly massless. And the masslessness means the photon travels at exactly c, has zero proper time, and has no valid reference frame. The second consequence of zero proper time is the behavior of light in different media. In vacuum, light travels at c. In a medium, glass, water, a gas light travels at a speed less than c. The ratio of c to the speed of light in the medium is the refractive index. In glass, the refractive index is approximately 1.5, meaning light travels at approximately 2/3 of c through glass. But the photons that travel through glass are not simply slowed down like a car driving through mud. The photons still travel at c between interactions with the atoms of the glass. What changes is the rate of the interactions. Photons in glass are constantly being absorbed and re-emitted by atoms, and the net effect of these absorptions and re-emissions is that the beam of light takes longer to traverse the glass than it would in vacuum. The average speed of propagation is less than c, but each individual photon travels at c between interactions. Each absorption and re-emission is a new photon event. The absorbed photon ceases to exist when it is absorbed by an atom, and a new photon is created when the atom emits. The new photon is not the same photon as the absorbed one. It has zero proper time from its emission to its next absorption, just as the original photon had zero proper time. The light that emerges from the glass is not the same light that entered. It is a succession of photon creation and annihilation events, connected by the emission and absorption processes in the atoms of the glass. This photon picture of light in media is more complex than the classical wave optics picture, but is more fundamentally correct. The refractive index emerges from quantum electrodynamics as a consequence of the scattering amplitude for photon-atom interactions. The beautiful mathematical structure of quantum electrodynamics, developed by Feynman, Schwinger, and Tominaga in the late 1940s, describes all of these photon-atom interactions with extraordinary precision. The third consequence of zero proper time is the connection between the photon and the causal structure of spacetime. The light cone at any event in spacetime, the set of all events that can be causally influenced by that event, And the set of all events that can causally influence that event is defined by the null geodesics passing through that event. The light cone is the boundary between the causal future and causal past of an event and the events that are causally disconnected from it. The photon's worldline is a null geodesic and therefore lies exactly on the light cone. The photon is, in a precise sense, the boundary of causality. Events that can influence each other must be connected by worldlines that lie inside the light cone worldlines of massive particles traveling at less than c. The photon traveling exactly at c defines the boundary of what is causally possible. This boundary role of the photon is not a coincidence. It is a consequence of the fact that the photon is the carrier of the electromagnetic force, which is the force that dominates macroscopic causal interactions. The boundaries of causal influence in the universe are set by electromagnetic signals, by light, and the photon travels at exactly the speed that defines those boundaries. The causal structure of space-time, the light cone, is a fundamental geometric feature of the Minkowski metric. It is the structure that preserves causality. Events inside the past light cone can influence the present event. Events inside the future light cone can be influenced by the present event, and events outside the light cone are causally disconnected. The speed of light is the constant that defines the light cone, and the photon is the particle that travels at exactly that speed. If the photon had even a tiny rest mass, the light cone would be slightly different from the photon's trajectory. The photon would travel at slightly less than c, and the causal boundary, still defined by c, would be a different geometric structure from the photon's worldline. The causal structure of space-time and the trajectory of the photon would separate. The masslessness of the photon keeps them together. The photon is the physical realization of the causal boundary. Let me now describe the quantum mechanical properties of light that make it even stranger than the classical picture suggests. In quantum mechanics, light is quantized. It comes in discrete packets called photons, each with energy E equals h bar times omega and momentum P equals h bar times the wave vector k. The energy and momentum are related to the frequency and wavelength of the light. Energy is Planck's constant times the frequency, and momentum is Planck's constant divided by the wavelength. The photon is a spin, one particle, with two possible polarization states corresponding to the two transverse polarizations of a classical electromagnetic wave. There is no longitudinal polarization state for a massless photon. This is a direct consequence of the masslessness. A massive spin, one particle has three polarization states, including a longitudinal state, while a massless spin, one particle has only two. The two polarization states of the photon can be described in two bases. The linear basis, in which the photon is polarized in one of two orthogonal directions, or the circular basis, in which the photon carries angular momentum of plus or minus h bar along its direction of propagation. The circular polarization states correspond to left and right circularly polarized light, which carry angular momentum to matter that absorbs them. The absorption of circularly polarized light, arouse what la what nik la what la what nik ahort my ha what my ha ahor lai ha my ha ha ahu aha a can han in pp. The absorption of circularly polarized light transfers angular momentum to the absorbing material, producing a torque. The photon's spin, one character, and its masslessness together constrain the form of the electromagnetic field. The electric and magnetic fields must be perpendicular to the direction of propagation and to each other, with magnitudes related by E equals CB. This is the transverse nature of electromagnetic waves, which follows from Maxwell's equations and from the masslessness of the photon. In quantum electrodynamics, the interaction of light with matter is described in terms of photon creation and annihilation operators. When an atom absorbs a photon is annihilated, and the atom transitions to a higher energy state. When an atom emits a photon is created and the atom transitions to a lower energy state. These creation and annihilation operations are described by the Fock space of photon states, in which the number of photons is not fixed but can change through interaction with matter. The vacuum state in quantum electrodynamics, the state with no photons, is not empty. It contains quantum fluctuations of the electromagnetic field, virtual photon pairs that are continuously being created and annihilated. These vacuum fluctuations produce the Casimir effect. Two perfectly conducting uncharged plates placed in vacuum attract each other because the vacuum fluctuations between the plates are constrained to have wavelengths that fit between the plates, while the vacuum fluctuations outside have a full range of wavelengths. The excess energy density of the outside vacuum relative to the constrained inside vacuum produces an attractive force. The Casimir effect has been measured experimentally with high precision, and it confirms the existence of vacuum fluctuations and the role of virtual photons in the quantum vacuum. The Casimir force between two conducting plates separated by distance d is approximately 1.3 times 10 to the minus 27 Newton times meters squared divided by the fourth power of d. The virtual photons in the Casimir effect are not the same as real photons. They are off-shell, meaning their energy and momentum do not satisfy the relation E equals pc. They are ephemeral quantum fluctuations that borrow energy from the vacuum for a brief time, consistent with the energy-time uncertainty relation. Delta E times delta T is greater than or equal to h bar over 2. They do not have the zero proper time property of real photons because they are not on the mass shell. The distinction between real photons and virtual photons is one of the most important and most often misunderstood distinctions in quantum field theory. Real photons are on shell. Their energy and momentum satisfy E equals pc, exactly. They propagate freely through space, interact with matter through photoelectric absorption and Compton scattering and other processes, and can be detected by physical detectors. Virtual photons are off-shell. They exist only within Feynman diagrams, as internal lines that connect vertices representing real particle interactions. They are mathematical tools for calculating interaction amplitudes, not physical particles that can be directly detected. The Coulomb force between two charged particles, the electric force that holds atoms together and drives chemistry, is mediated by virtual photons, not real photons. The electron that orbits the nucleus in a hydrogen atom exchanges virtual photons with the proton, and the exchange of virtual photons is what produces the attractive Coulomb force. But these virtual photons are mathematical descriptions of the quantum field interactions, not physical particles traveling between the electron and the proton. This is one of the deepest conceptual subtleties of quantum electrodynamics. The everyday electrostatic and magnetostatic forces that we experience are mediated by virtual photons, while the light that we see is mediated by real photons. The same particle, the photon, is responsible for both, but in qualitatively different ways. The 12 principles in my book address exactly this: the relationship between the mathematical description of quantum field theory and the physical reality that it describes, and how to navigate the subtle distinctions between real and virtual particles, between on-shell and off-shell, between the observed world and the mathematical framework that predicts it. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now describe one more property of light that is strange, but whose full strangeness is often not appreciated: the wave-particle duality of light, and what quantum mechanics actually says about it. Before quantum mechanics, light was understood as a wave phenomenon. Maxwell's electromagnetic theory, published in 1873, provided a complete classical description of light as oscillating electric and magnetic fields. The wave nature of light was confirmed by Young's double-slit interference experiment, by the diffraction of light around obstacles, by the polarization of light, and by Maxwell's prediction confirmed by Hertz's experiments that radio waves and visible light are both electromagnetic waves differing only in frequency. Then, in 1905, Einstein proposed that light is quantized in discrete packets, photons, each carrying energy E equals h bar omega. This was not a contradiction of the wave description, but an addition. Light has both wave-like properties, exhibited in interference and diffraction, and particle-like properties, exhibited in the photoelectric effect and Compton scattering. The wave-particle duality of light seems paradoxical. How can something be both a wave and a particle simultaneously? Quantum mechanics resolve the apparent paradox by providing a unified framework in which both descriptions are special cases. The quantum state of a single photon is a quantum state, a vector, in a Hilbert space that describes the photon's mode function. The mode function is a solution to Maxwell's equations with specified frequency, wave vector, and polarization. The quantum state also specifies the number of photons. A single photon state has exactly one photon in the specified mode. When you perform a measurement on the photon, the outcome depends on what you measure. If you measure the position of the photon, if you place a detector at a specific location, the photon either arrives at the detector or it does not. Each individual photon gives a localized detection event. One click of the detector at one specific location. This is the particle behavior. If you allow many photons to be detected and look at the distribution of detection positions, the distribution follows the intensity pattern of the classical electromagnetic wave. Bright regions of the wave correspond to high probability of detection. Dark regions correspond to low probability. This is the wave behavior. The resolution of the apparent paradox is that the wave description gives the probability distribution for detection outcomes, while each individual detection is a particle event. The wave is not a physical wave of matter or of some substance. It is a probability amplitude, a complex number whose modulus squared gives the probability of finding the photon at a given location. Interference and diffraction occur because probability amplitudes can constructively or destructively interfere, just as classical wave amplitudes do. But this resolution is not complete in the sense of explaining what the photon is between measurements. Between the emission event and the detection event, is the photon a wave or a particle? In the Copenhagen interpretation, this question has no answer. The photon has neither a definite wave nature nor a definite particle nature between measurements. It has a quantum state which encodes the probabilities of various measurement outcomes but does not describe a definite classical object. In the many worlds interpretation, the photon is always in a specific quantum state that evolves according to the Schrödinger equation. The wave-particle duality is a feature of the quantum state's behavior when it interacts with a measuring apparatus. The quantum state of the photon plus detector branches into one branch for each possible detection outcome, and each branch is equally real. In the Bohmian interpretation, the photon has a definite position at all times, but it is also accompanied by the wave function, which guides the photon's motion. The photon is a particle, but its trajectory is determined by the wave function through the guidance equation. The wave-particle duality is resolved by having both a real particle and a real guiding wave. Each of these interpretations preserves the experimental predictions of quantum mechanics. Each gives a different picture of what the photon is between measurements. The question which is correct is one of the deepest open questions in the foundations of physics. Let me now describe the specific properties of light that connect the zero proper time to the deepest principles of the standard model of particle physics. The photon's zero rest mass is not an accident. It is a consequence of the U1 gauge symmetry of electromagnetism. Electromagnetism is a gauge theory. Its equations are invariant under a specific transformation that multiplies the electron field by a position-dependent complex phase without changing any observable physical quantity. This local U1 symmetry is the mathematical expression of electric charge conservation. In quantum field theory, local gauge symmetries require the existence of massless spin. One bosons gauge bosons that carry the corresponding force. The U1 gauge symmetry of electromagnetism requires the photon to be exactly massless. A mass term for the photon would break the U1 gauge symmetry, because the mass term couples different components of the gauge field in a way that is not invariant under the local phase transformation. This is the deep reason why the photon has zero rest mass, zero proper time, and a null geodesic worldline. The gauge symmetry forces these properties. The photon is not just a particle that happens to be massless. It is the gauge boson of electromagnetism, and its masslessness is required by the fundamental symmetry of the electromagnetic interaction. The contrast with the W and Z bosons, the gauge bosons of the weak nuclear force, illuminates this. The weak force also has a gauge symmetry, SU2, and it also requires massless gauge bosons if the symmetry is exact. But the Higgs field breaks the SU2 symmetry spontaneously, giving the W and Z bosons masses of approximately 80 and 91 GeV respectively. The photon remains massless because the electromagnetic U1 symmetry is not broken by the Higgs field. The discovery of the Higgs boson at CERN in 2012 confirmed the Higgs mechanism, and in a new way, confirmed the photon's masslessness. The Higgs boson interacts with particles in proportion to their rest mass. Since the photon has zero rest mass, the Higgs boson does not interact directly with photons at tree level. The photon's freedom from direct Higgs coupling is a direct consequence of its masslessness, which is a direct consequence of the unbroken U1 symmetry. The Casimir effect is a direct demonstration that the electromagnetic field has structure even in the vacuum. Two uncharged, perfectly conducting plates placed in vacuum attract each other with a force that depends only on the plate separation and the fundamental constants h bar and c. The force per unit area equals pi squared h bar c divided by 240d to the fourth power, where d is the plate separation. This formula was predicted by Casimir in 1948 and confirmed experimentally by Lamoureux in 1997. The Casimir force arises from the zero-point energy of the electromagnetic field, the vacuum fluctuations that persist even in the ground state. The plates constrain the modes of the electromagnetic field that can exist between them, changing the vacuum energy density between the plates relative to the outside. The difference in vacuum energy density produces an attractive force. The vacuum fluctuations that produce the Casimir effect are virtual photons off-shell field fluctuations that exist in the quantum vacuum. They are not the same as real photons. Their energy and momentum do not satisfy E equals PC. But they are a physical consequence of the same photon field that produces real photons when it is excited. The distinction between real and virtual photons is fundamental. Real photons propagate freely along null geodesics, accumulate zero proper time, can be detected by physical detectors, and carry information. Virtual photons are off-shell field fluctuations that appear as internal lines in Feynman diagrams, mediate the electromagnetic force between charges, and contribute to the Casimir effect and the Lamb shift. The everyday electrical and magnetic forces are mediated by virtual photons, not particles traveling between charges, but quantum field correlations in the vacuum. Let me now describe the wave-particle duality in its most precise quantum mechanical form, because the zero proper time of the photon is built into its wave-like description. The quantum state of a photon is not a classical wave. It is a quantum state, a vector in a Hilbert space that encodes the probabilities of all possible measurement outcomes. The photon's quantum state can be described by its mode function, which is a solution to Maxwell's equations with definite frequency, wave vector, and polarization. The mode functions satisfy the dispersion relation omega equals c times the magnitude of k, exactly the relation that corresponds to propagation along null geodesics at the speed c. This is the key connection. The wave function of a photon is built from modes that propagate along null geodesics. The zero proper time of the photon is built into the mathematical description of the photon's quantum state from the start. The photon's wave function propagates at c along null geodesic directions, and the photon itself, when detected, is detected as a discrete particle event at a specific location. The wave nature and the particle nature are both consequences of the same quantum field description. The double slit experiment with single photons demonstrates this clearly. Each photon is detected as a single click at a specific location particle behavior, but the distribution of clicks over many trials follows the interference pattern predicted by Maxwell's equations wave behavior. The single photon passes through both slits simultaneously in the sense that its wave function has non-zero amplitude at both slits. The two components of the wave function interfere, and the probability of detection at each location is determined by the modulus squared of the interfering probability amplitude. The probability amplitude for a photon to travel from the source to a specific detector location is the sum over all paths from source to detector, weighted by the phase accumulated along each path. The phase is proportional to the path length in units of the photon's wavelength. This sum over paths, or path integral description, developed by Feynman, is the most complete statement of wave-particle duality. The photon takes all possible paths simultaneously, accumulating a phase along each path, and the interference of the phases from different paths determines the probability of detection. The paths that photons actually follow the null geodesics of spacetime are the paths that contribute most to the path integral in the limit of short wavelengths. This is the quantum explanation of geometric optics. In the short wavelength limit, the path integral is dominated by the paths of stationary phase, which are the null geodesics. The photon follows null geodesics not because it has been told to, but because in the short wavelength limit, the contributions to the path integral from non-null paths cancel by interference. This is one of the most beautiful results in quantum optics. The fact that light travels in straight lines in geometric optics and bends around massive objects as described by general relativity emerges from the interference of probability amplitudes for all possible photon paths. The null geodesic is the path of stationary phase in the limit of short wavelengths. The photon's zero proper time, the fact that its worldline is a null geodesic, is therefore not just a consequence of its masslessness. It is the deepest statement about why light behaves the way it does. It follows the paths of stationary action, which are the null geodesics, because those are the paths along which the quantum probability amplitudes add constructively rather than canceling by interference. The strangest fact about light, developed to its full depth, connects the zero proper time of the photon to the gauge symmetry of electromagnetism, to the Higgs mechanism that gives mass to the W and Z bosons while leaving the photon massless, to the Casimir effect as a demonstration of electromagnetic vacuum fluctuations, to the wave-particle duality as a consequence of quantum probability amplitudes propagating along null geodesics, and to the path integral as the deepest explanation of why light follows the paths it follows. All of these connections trace back to one fact. The photon is the gauge boson of the UA, gauge symmetry of electromagnetism, and that symmetry forces the photon to be massless, to travel at c, to have a null geodesic worldline, and to accumulate zero proper time on any journey of any duration. The photon has zero proper time. The emission event and the absorption event are separated by zero space-time interval in the Minkowski metric. In the geometrical language of the block universe, the photon's worldline has zero length. What does this mean for the photon's experience of the universe? The answer is that the question is, strictly speaking, ill-posed. The photon has no valid reference frame, and questions about the photon's experience presuppose a reference frame. But we can ask a related and well-posed question. What is the geometry of the photon's worldline in the block universe? The answer is that the photon's worldline is a null geodesic, a curve in the spacetime manifold along which the metric interval is 0. Null geodesics are the limiting case between time-like geodesics, along which massive particles travel and which have negative metric interval, and space-like geodesics, which connect events that cannot be causally connected and which have positive metric interval. In the Penrose conformal diagram representation of spacetime, null geodesics are represented as lines at 45 degrees. The entire history of a photon, its world line from emission to absorption, is a straight line at 45 degrees in the conformal diagram. In the conformal diagram, the photon's world line looks like a line of 0 length. The emission event and the absorption event are at the same conformal location because the conformal transformation that produces the diagram maps the null geodesic to a 0-length interval. Roger Penrose, who developed the conformal diagram technique, described this as the photon being able to see all of its history in an instant, except that the photon has no experience of time in which to have this instant. The null geodesic is the ultimate limiting case of temporal experience. It is the case in which temporal experience is entirely absent. The photon's position in the geometry of space-time is therefore extraordinary. It connects events that are causally related, that lie on each other's light cones by a path of 0 space-time length. It carries information, energy, and momentum across vast distances of space and time while experiencing neither space nor time. It is, in the complete four-dimensional picture of the universe, a connection between events that are, in the Minkowski metric, 0 apart. This is the strangest fact about light that you have probably never heard. Not the speed of light, not the bending of light by gravity, not the wave-particle duality. The strangest fact is that light's journey from source to destination spans 0 time and 0 distance in the precise mathematical sense of the Minkowski metric, and that this 0-length connection is what carries information across the visible universe, what enforces the causal structure of space-time, and what defines the limits of what can influence what in the cosmos. The photon is not just a particle of light. It is the physical embodiment of the causal boundary of space-time. It travels at the speed that defines what can and cannot influence what. It exists at the intersection of the possible and the impossible. Possible because it can travel from source to destination, impossible because it cannot have a reference frame. It is the exception that defines the rule, the limit that reveals the structure, the strangest object in the universe precisely because it connects events without traversing the space and time between them. Let me now develop what this means for how we experience the universe around us. Every photon that has ever entered your eyes connected you to its source through a null geodesic, a path of 0 Minkowski space-time length. The photons from the sun that illuminate your day traveled 150 million kilometers in 8 minutes in coordinate space and time, but accumulated 0 proper time on the journey. The photons from a distant star that you see on a clear night may have traveled thousands of light years in coordinate time, but each one arrived at your retina having accumulated 0 proper time. The photons from a galaxy, 1 billion light years away, that reach a telescope tonight, connected their galaxy to the telescope through a null geodesic, spanning 1 billion years of coordinate time and 0 proper time. This means that the universe you see around you, everything visible to the naked eye, to any telescope, to any detector of electromagnetic radiation, is connected to you through paths of 0 space-time distance. Not through distances that seem large from our time-like perspective, but are actually small from some other perspective. Through paths of genuinely 0 space-time distance in the Minkowski metric. The Minkowski metric is the mathematical structure of space-time that special relativity establishes. The 0 space-time distance of the null geodesic is not a mathematical artifact. It is a physical fact about the space-time structure that connects events in the universe. Let me now describe the modern experiments with individual photons that make the 0 proper time property experimentally vivid because the abstract mathematics becomes concrete when you can manipulate single photons in a laboratory. The first single photon source was demonstrated in 1977 by Kimball, Dagenais, and Mandel using fluorescence from a single sodium atom. They showed that the photon statistics from a single atom exhibit anti-bunching, the tendency of photons to be emitted one at a time, rather than in random bunches as a classical light source would produce. Anti-bunching is a quintessentially quantum phenomenon. It shows that the electromagnetic field around a single atom cannot simultaneously emit two photons, because after emitting one photon, the atom must be re-excited before it can emit another. The single photon nature of the emission process was directly confirmed. Modern single photon sources include nitrogen vacancy centers in diamond, single quantum dots, and parametric down conversion, a process in which a pump photon is converted into two lower energy photons with correlated properties. Parametric down conversion is particularly useful for quantum optics experiments because it produces pairs of entangled photons, allowing the quantum state of one photon to be inferred from measurement of the other. In experiments using single photons from these sources, the zero proper time of the photon manifests as perfect temporal coherence. A single photon from a well-defined source has a definite frequency and maintains its quantum state perfectly during propagation. Two photons from identical sources propagating along identical paths will exhibit perfect quantum interference when they arrive at a beam splitter. Simultaneously, they will always exit the beam splitter together rather than separately, a phenomenon called the Hong-Ou-Mandel effect. The Hong-Ou-Mandel effect, first demonstrated in 1987 by Hong-Ou and Mandel, is one of the most distinctive signatures of the quantum nature of light. When two identical photons arrive at a 50-to-50 beam splitter at the same time, they always exit together from the same output port, even though classically you would expect them to exit independently with equal probability. The quantum interference of the photon wave functions at the beam splitter causes the amplitudes for the two photons to exit from different ports to cancel. The effect requires that the two photons be indistinguishable in all their properties, same frequency, same polarization, same arrival time. Any distinguishing information, any which path information destroys the interference. The Hong-Ou-Mandel effect demonstrates the wave-like nature of individual photons in a particularly clean way. Each photon's wave function spans both input ports of the beam splitter simultaneously. The wave functions of the two photons interfere at the beam splitter. The interference is constructive for the two photon states, where both photons exit from the same port, and destructive for the states where they exit from different ports. This is quantum interference between single photons, directly demonstrating the zero proper time property. The photons maintain their quantum coherence perfectly during propagation and exhibit interference that depends on the precise timing and path length of their journey. The precision with which Hong-Ou-Mandel experiments can detect path length differences is extraordinary. Since photons propagate at c with zero proper time, any difference in the path lengths of the two photons, even a difference of a few micrometers, will introduce a time difference that makes the photons distinguishable and destroys the interference. Hong-Ou-Mandel interferometers have been used to measure path length differences with sub-femtosecond 10 to the minus 15 second resolution, corresponding to path length differences of a few hundred nanometers. This sub-femtosecond temporal resolution is possible precisely because of the zero proper time of the photon. The photon maintains its quantum state with perfect fidelity during propagation. Any relative delay between the two paths appears as a relative time difference at the beam splitter, and the interference visibility degrades as the delay increases. By measuring the interference visibility as a function of the path length difference, the width of the photon's wave packet in time can be measured with femtosecond precision. These Hong-Ou-Mandel interferometry experiments have been extended to photons separated by large distances. In one remarkable experiment by Pan and collaborators in China, photon pairs from parametric down conversion were distributed through optical fibers over distances of tens of kilometers, and Hongou-Mandel interference was observed between photons that had traveled these long distances. The zero proper time property was preserved. The photons' quantum states were maintained during propagation, and interference with visibility exceeding 90% was observed after transmission through 5 0-kilometer fiber links. This long-distance preservation of quantum coherence is the basis for quantum repeaters, the proposed devices that will extend quantum communication over intercontinental distances by entanglement, swapping, and quantum teleportation. The entire technology of quantum networking, which is expected to be a major technological development of the next few decades, depends fundamentally on the zero proper time of photons. The fact that photons maintain their quantum states perfectly during propagation allows quantum information to be transmitted faithfully over long distances. The most ambitious demonstration of quantum photon properties over long distances used the massless satellite, a Chinese quantum science satellite launched in 2016. Massless distributed entangled photon pairs between ground stations in China separated by more than 1,200 kilometers, demonstrating Bell inequality violations and quantum key distribution over record distances. Each entangled photon maintained its quantum state, including its entanglement with its partner during propagation through hundreds of kilometers of atmosphere from satellite to ground station. The quantum coherence was maintained because of the photon's zero proper time. The photon's quantum state does not evolve during propagation in the absence of interactions. The implications of these experiments for our understanding of the photon's zero proper time are specific and profound. The photon that is entangled with its partner at the moment of pair production maintains that entanglement perfectly during propagation, regardless of the distance. When the photon is measured, the measurement reveals the quantum correlation with the partner photon instantaneously, regardless of where the partner photon is. This non-locality, the instant correlation between distant measurements on entangled photons, is possible because the photons maintain their quantum states perfectly during propagation, and the perfect maintenance is a consequence of the zero proper time. In a universe where photons accumulated proper time during propagation, the quantum state would evolve during the photon's journey, potentially disrupting the entanglement. The fact that entangled photons maintain their correlations over distances of hundreds of kilometers is a direct experimental demonstration that photons do not accumulate proper time during propagation, that the zero proper time property is physically real and not merely a mathematical limit statement. The strangest fact about light is thus confirmed not just by the abstract mathematics of the Lorentz transformation, but by the concrete physics of Hongou-Mandel experiments: quantum key distribution over fiber and satellite-based quantum communication. The photon travels without experiencing time. The universe connects its emission events to its absorption events through zero-length null geodesics, and this property, far from being an abstract curiosity, is the physical foundation for the most advanced quantum optical technologies in the world today. A massive particle propagating through a medium can accumulate phase and lose quantum coherence through interactions with the environment. The photon, with zero proper time, maintains perfect quantum coherence during propagation until it is absorbed or scattered. This is the physical basis for long baseline astronomical interferometry. The Event Horizon Telescope combined photons from the same source detected at telescopes around the world, treating them as coherent, and produced images with an effective angular resolution of 20 microarcseconds. It is also the basis for quantum cryptography and quantum communication over satellite links at distances exceeding 1,000 kilometers. The gravitational lensing of light, the bending of photon paths around massive objects, which produces the beautiful arcs and multiple images seen in deep field images from Hubble and Webb, does not change the zero proper time property. Even as the null geodesics curve in the gravitational field of a galaxy cluster, the photons following them accumulate zero proper time. The zero proper time is a property of null geodesics in any space-time, curved or flat. Every photon is a zero-length connection to the universe. Every beam of light is the universe touching you at zero space-time distance. Every moment of vision is the universe making contact with you through a path that, in the geometry of space-time, is no path at all. A connection that spans billions of years of coordinate time while experiencing zero time, that spans billions of light years of coordinate space while experiencing zero distance. That is the strangest fact about light. That is what the Minkowski geometry of space-time says about the most abundant quantum in the universe. That is the fact that, when fully absorbed, changes how you see every photon that enters your eyes. Everything we see, every photon that has entered our eyes from the beginning of human vision, arrived with zero proper time accumulated on its journey. The light from the sun that is warming the earth right now has experienced no time since it left the sunday. The light from a star 1,000 light years away that reaches a telescope tonight has accumulated no time on its 1,000-year journey. Every beam of light is, from the photon's excluded but limiting perspective, instantaneous. We are connected to the universe through light. The information about everything we have ever seen, everything we know about the cosmos beyond the earth, has come to us through photons. And every one of those photons arrived at zero cost in proper time, connecting us to events across the universe through null geodesics, through connections that span zero space-time distance despite spanning billions of light years in coordinate space. That is the strangest fact about light. That is what the Minkowski geometry of space-time says about the most abundant quantum in the universe. And it is a fact that, when fully absorbed, changes how you see every photon of light that enters your eyes. The 12 principles I have assembled for understanding the fabric of reality include exactly this kind of engagement: taking the physics seriously all the way down, following the mathematics to its consequences, and finding that the conclusions are stranger and more beautiful than ordinary experience suggests. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What does it change for you to know that every photon you have ever seen arrived without accumulating any time on its journey? Tell me in the comments. If this changed how you think about light, about time, and about the connection between you and the universe that light makes possible, tell me in the comments. Tell me whether the zero proper time of the photon makes light feel more or less real to you, and whether the idea that the photon has no valid reference frame changes how you think about what it means to be a physical object. And subscribe if you want to keep going into the places where the physics of light and the geometry of space-time reveal the most fundamental properties of the universe we inhabit.